this idea of stereoisomerism from the context of the bigger picture in terms of the bigger world. This idea that stereoisomers are everywhere, there are many of them, and the relationships are not particularly easy to see. We have already dealt with things like constitutional isomers, where we put the atoms together in different ways to make different molecules from the same pieces, the same Lego bricks, if you like. We then delved into stereoisomers starting in chapter 4, where we talked about cis and trans when we did the cyclohexanes and the cyclopropane, stuff like that. In chapter 5, we've introduced this idea of mirror image relationships, and if they're mirror images and you cannot put one on top of the other, they're non-superimposable, they are not the same compound. They are then said to be enantiomers, and that's the relationship. They are stereoisomers related as such. Now, enantiomers have to be the mirror image. If they're not the mirror image, they must be something else, and that's where the word diastereomer comes in. So these words need to be understood so that we can handle them and we can understand them. Diastereomers are stereoisomers in a series that are not related as enantiomers. So when we start looking at pictures like this, as we did on Wednesday, you can see now that we have more complexity, no doubt. And many of you are interested in biological stuff, which is that, chemistry is a foundation for that. This is the beginning of it. You have to be happy with this stuff. So on the left, I've got my different pictures here. I've got my cyclohexanes with the two different groups on. And in the past, we've written this either way and said that they were the same thing. They would both count as a cis cyclohexane type system. But now we're saying there's a difference. Now we are arguing that because we now have chiral centers here and here, this is not the same. They are non-superimposable mirror images. And if you worked out the R and the S, which we did, and we have done in recitation this week, and we can do more next week, you'll find that this is the 1R2S and this is the 1S2R. You notice the mirror image relationship. If this is R, this must be S. If this is S, this must be R. Easy enough. If you can calculate or work out those things, that's really helpful. It'll speed things up, and you'll be able to work out what the relationships are without necessarily having to be really good at seeing things in 3D. Well, those two are fairly obvious, and over here I think it's fairly obvious. These are the trans isomers that we drew in chapter 4. And we can see here up, down, and we can see here down, up. And in chapter 4, we said, okay, they're the same thing. In fact, they do have the same energy, but they're not the same molecule anymore because they are non-superimposable mirror images, and therefore they are enantiomers. I can see 4. Can anybody else give me a fifth? Can we come up with a fifth possibility? No, you cannot. It's impossible. They are the only possible ways you can put this molecule together to get 4 stereoisomers, right? So we're going to build a rule today, 2 to the n. If you count n stereocenters, you will get 2 to the n stereoisomers as your maximum number. Sometimes you get fewer, and you have to be aware of that. So right now, be aware that we're making things more complex because we have to, and we should be happy with where the R and the S comes from, so we can start talking about the relationships. Now, these are enantiomers, no doubt. These are enantiomers, no doubt, because they are mirror images. These two are not mirror images, but they are part of the same series. That's where the word diastereomer comes into play, because we need something to relate them. So those two are diastereomers, these two are diastereomers. In fact, anything that's not related as an enantiomer is a diastereomer. What we'll try and do today is draw these things, relate them, turn them around, manipulate them, see them from different angles, and be good at this and be confident in what we're doing. Again, I'm a chemist. I like this stuff, obviously, but most of you are related to biology, and your molecules are way more complicated than my molecules. So we have to build on that complexity. Here we have 3 chiral centers. On my exams, you typically, you might see 3. I'm not going to give you 4. That would take too long to do, but you might see 3. If you think now of the possibilities, I can put them all as wedges. I can put them all as dashes. That gives me a pair of enantiomers. I could start breaking things up. I could put the chlorine as a dash, leave 2 of them where they were. That's a different molecule. That molecule there is not the same as over here or over here. The stereocenters changed. We have a different identity. We can make its enantiomer. Thinking about the quiz, thinking about the homework coming up, the enantiomer is simply the mirror image. Make sure it's the mirror image, but non-superimposable. Chlorine is a wedge. Methyl and hydroxyl as dashes. They're different molecules. They're related as non-superimposable mirror images, therefore they are enantiomers. Down at the bottom, all we're doing here is exhausting the permutations, the possibilities of putting these things together to get different molecules that are related as stereoisomers. If I start changing things around, if I start moving my groups over here, they're no longer stereoisomers, they're constitutional isomers. These are all bonded in the same way, in the same pattern, 1, 2, 3. They just differ by their orientation in space, which is the definition of a stereoisomer. Down at the bottom, to finish this off, I've got the last 2. And the reason they're collected in boxes like this is because that's an enantiomeric pair, that's an enantiomeric pair, as is that, as is that. But then I have to worry about relationships between all the other systems. The relationship, for example, between this and this. Are they mirror images? No, but they are stereoisomers. Yeah, all the connectivity is the same, it's just a difference in direction in space. So because, for example, this hydroxyl is pointing as a dash and this one is a wedge, they're not enantiomers. They are diastereomers. So you'll be able to do that relationship for any of the systems there that you cannot relate as enantiomers. We will do this in recitation next week. This is a big part of Monday and Wednesday, and it really is. I mean, I emphasize it is so important to be able to do this quickly. Questions? I'm trying to slow down today. I'm doing my best to keep this, you know, if I get into 6 today, I do. If I don't, that's up to you. There's a lot of stuff here. There is a general rule. If you have n chiral centers, the maximum number of stereoisomers you can get is 2 to the n. So you've got 1 stereocenter, 2 to the 1, 2. You get 2 enantiomers. You get 2 stereocenters, you get 4 possibilities. 2 pairs of enantiomers, the rest of them are diastereomers. And you can take that to the extreme here with something biological like cholesterol, in which we have 1, 2, 3, 4, 5, 6, 7, 8 chiral centers. So 2 to the 8, if you work it out, is 256. There are 256 possible stereoisomers of cholesterol in which you have all the same bonding patterns, everything's in the same place other than the direction in space. So if I want to make a diastereomer of this guy, I might take that and make it into a wedge. That's no longer cholesterol. That is a diastereomer of cholesterol which will have different properties. Michaela. Wow. They should pay me more. No, they won't. If you change one of those stereocenters without changing everything else, you can't have enantiomers. If you change all the stereocenters for the opposite, wedge to dash or dash to wedge, you'll make the enantiomer. And there will be an enantiomer possible, maybe not in nature. Again, you can think about chemical evolution and chemical biology and how these things come about to serve a purpose. Of those 256 isomers, only 1 actually exists in nature. Yeah, you can make the others. They might have some interesting pharmacological properties, but they don't exist in nature. So keep an eye on that rule, 2 to the n. I will show you a caveat in a second where it doesn't quite work like that, but for the most part, you're looking at 2 to the n to give you the maximum number of stereoisomers possible when you have n chiral centers. This, for many of you, is where you need to go. Is biochemistry, is the idea of the carbohydrates, the idea of the amino acids, which are all chiral, except 1. This idea that nature has produced these polyhydroxylated compounds with different configurations of their chiral centers to do different jobs. We use in our biochemistry, obviously, a lot of glucose. So this one will be something, you'll probably memorize that structure in the future for biochem. Mannose, likewise, we use a lot of. Galactose we use a lot of. We don't use so much of this, but other organisms do, for example, bacteria. So these compounds become very important in terms of trying to mimic them, trying to make compounds that look like them, so that we can maybe prevent processes from happening and cure disease. So what is happening here is the first look at what we call a Fischer depiction. That's a big part of today, trying to understand where Fischer depictions come from and how to draw them. And this now is stereochemical information in a different format. This has been around for a long time, and it still works, so you'll have to get used to this. You'll see now that in this series, I have 1, 2, 3, 4, 5, 6, 7, 8 isomers. But I have 4 chiral centers, so the missing 8 are the enantiomers of these things. There are 16 of these things that you'll have to be comfortable with in biochemistry if you get that far. So now we're talking about more complex molecules. We're into the biological world, and this is, I think, interesting. 2 to the n is the max. Sometimes you don't get 2 to the n. You might get 1 fewer. And in recitation, certainly, and I think in class also, we've been talking about the difference between symmetry and asymmetry. Symmetry, obviously, is when you can fold something in half, for example, and the left matches the right. And what that says is you don't have 4 different things attached to your carbon, and so therefore it can't be chiral. That's a key test for working out chirality. But within systems that do seem to have chiral centers, sometimes you can get symmetry. And this is where this comes in. We're going to say now that the trans-cyclohexane and the cis-cyclohexane, you look at their possibilities. There is no symmetry through that plane in that molecule, because this is pointing down and this is pointing up. That's okay? There is no symmetry here between those two because the methyls match. And you might say, well, isn't this a chair? And they'll say, yes, but those chairs are always moving. So what you're seeing is an average, and that average will have a mirror plane. And so therefore it will have this property. There are some possibilities for symmetry that we haven't seen before, rotational symmetry. If you take this molecule and turn it up like that, this methyl ends up on that methyl. So there is some symmetry within that system, but it's not going to damage the chirality. So we might see here something called a rotational axis of symmetry versus a plane of symmetry, and hopefully we're okay with that. if not ask. So here's a problem. When we make a molecule like this, the argument is that looks like a chiral center, and that looks like a chiral center also, because they do have 4 different things attached: an H, a methyl, a CH2, and a C with a methyl attached. Those are 2 chiral centers. But that molecule is symmetrical. So far we've said that chirality is all about asymmetry. But now we have a system in which, yes, it looks like it has chiral centers, but the whole molecule itself is symmetrical. And we're going to give this a term in a second to describe it, but that's the test. If you have an internal plane of symmetry in your molecule, regardless of whether it has chiral centers or not, it won't be chiral. It won't have an optical activity. It won't have an alpha D value. So this is a term called meso, okay, down here. Meso suggesting a mirror plane inside the molecule. And we can see this with some real molecules here. The idea that the trans isomers, this is pointing down, this is pointing up. They're not overlapping each other. So this molecule can't be symmetrical through a plane. Same with this guy. We already defined these 2 as both being trans isomers, but now they're both enantiomers of that trans isomer. And over here we have the cis. And I think this is key. If you get this, you're in good shape. If I turn this molecule over so that my hydroxyls go into the plane like that, they should be the same molecule. Is that okay? If I turn this thing over, it's the same thing as that. Even though this is a chiral center, that's a chiral center, so is that, and so is that. But in reality, they are the same molecule, because you can put one on top of the other. So this would be said to be achiral because of this plane of symmetry. And when that arises, it's said to be a meso compound. So that's the asterisk. That's the situation where 2 to the n doesn't quite work. You get 2 to the n possibly minus 1 because of internal symmetry and because of the fact that what looks like a chiral compound isn't, because it has this plane of symmetry through the middle in which this matches this. There's more to it. I'll explain in a minute as we draw some pictures, but that's the basic idea. Go ahead. Yes. It does. Look at that. There's the line of symmetry right there. The cis isomer does. It's the trans that doesn't. Yeah? Ashley, quiet today. Good. Okay. Now, again, how important is this stuff? I don't have many chemists in this room. I have an awful lot of pre-something, an awful lot of bio-something, an awful lot of engineers. And these compounds now, and these representations are important. So we can see now a model, a picture of a molecule, which is butanediol. So there's 4 carbons, there's a hydroxyl, there's a hydroxyl. These are representations of that molecule. Very soon we'll be talking about alcohols and their nomenclature in detail, and the alkyl halides in detail, but that's a diol right now. In this system, it's important in this system because it's different. It's acyclic. This does not contain a cycle, so it might be more difficult to see. Acyclic, the plane of symmetry. At the top, I have a methyl group. At the bottom, I have a methyl group. That's important. If they're different groups, you can't have an internal plane of symmetry. They have to be the same. The top has to match the bottom. So in this system, I can put a hydroxyl to the left. Maybe it might be a wedge. Down here, I've got a hydroxyl to the right. Maybe that's a wedge also. That's one way of drawing one of those molecules. If you transpose that over here, there's your same methyl at the top, there's the same methyl at the bottom. Now, what's the relationship between these 2? This one on the left, this one on the right. They are enantiomers. This is pointing left, this is pointing right, this is pointing right, this is pointing left. You pick one up and try and put it on top of the other, it won't work. They're non-superimposable mirror images, so therefore they are enantiomers. Now all we've done to go to this other system over here is we've taken this bottom hydroxyl, broken it off, and put it on the right. You think about recitation this week with those big models I brought in, that's what we did to get to the other enantiomer, was take off 2 pieces, switch them, and that gave me the enantiomer. That's exactly the same operation here. So I've got now 2 hydroxyls that happen to be on the same side of the chain. And because my methyl is matching the methyl at the bottom, I have an internal plane of symmetry. The top matches the bottom. And that gives me what is described as the meso isomer of that molecule. Go on. Yes, you're looking for a plane of symmetry. No plane of symmetry, it's chiral, it's polypipe enantiomeric pair. So let's worry about this. Let's think about this in a bit more sort of fundamental detail. If here, let's say this is 2, it says it's the S it says it's the S stereocenter. And if this one's on the right over here, it says it's the R stereocenter. Here's the background to this. Now, the alpha D for this is 0. There is no optical rotation because of symmetry. That will be very important as a clue to work out what's going on here. Alpha D is 0. Now, how can alpha D be 0 if it contains what look like chiral centers? Surely the molecules are going to knock this piece of this light wave in different directions. But look at this. If this really is the mirror image of this, you have essentially two enantiomers in the same molecule. You have the R at the bottom and you have the S at the top of the same stereocenter. So you have in this mixture kind of a mixture, a 50-50 mixture of the R and the S. Again, if this was a bromine or a chlorine or something else, you couldn't have this property because it wouldn't be symmetrical. But you do. You have a symmetry center in the middle so that when the light hits this carbon, it gets bent X degrees maybe to the right. What happens when it hits this carbon at the top? It reverts back. It goes X degrees in the opposite direction. What's the overall outcome? 0. All right? So that's 0. Now, I'm going to define this, that we're going to call things like this racemic mixtures, but this is an internal racemic mixture. Racemic, R-A-C-E-M-I-C, racemic mixture. In other words, 50% of both of those chiral centers are present, and they cancel each other out. So alpha D becomes 0, even though that molecule has chiral centers. So meso is the odd one out. Meso is the situation in which you don't get an optical rotation because of the internal symmetry. It doesn't happen often, but you have to be on your toes to recognize when it does. Anybody? Come on. That's what we're going to do next. And that's the tricky part. You have to turn these pictures on their side. You have to turn them into Fischer, what we call Fischer depictions. You have to go backwards and forwards. This is absolutely difficult, no doubt. This will be very, very frustrating. So I have a situation now where if I have n chiral centers, I'll have 2 to the n stereoisomers, unless I have an internal plane, and then I have one fewer. That's called the meso situation. So let's get this out of the way. This is going to cause you pain. Okay? There's no doubt about that. Even the best students in the class will struggle with this stuff. Everybody does. So we're going back 120 odd years now to Emil Fischer, who was regarded as sort of the person who really started biochemistry in the 1880s, 1890s in Germany. And he won a Nobel Prize for his efforts in 1902. So he invented these things a bit before that, and they are still used. They are still the best situation we have, the best, most clear situation we have for multiple chiral centers in acyclic molecules, particularly carbohydrates and amino acids, which are a huge amount of biochemistry. And he devised something called a Fischer projection. If you understood Newman's, this wasn't so bad. If you didn't, this is nonsense. If you're okay with cyclohexanes and relationships between things like eclipsing and gauche and all that sort of stuff, this shouldn't be too much more of a problem. But this is a situation in which I'm going to ask you to be able to turn these things back into these things and vice versa, to make sure you can do it. It absolutely is a challenge to do this. So Fischer decided, well, you know, he worked out the structure of glucose. This was Nobel Prize winning stuff. He worked out the structure of glucose without any instruments that we have today. We have a huge number of instruments in Ward Beecher over there that allow you to work out molecular structure. He didn't. He worked it out by deduction, by very clever experiments, to say that the structure of D-glucose is this particular structure. And along with that came the idea that if I have multiple chiral centers like this one, and this one, which have 4 different things attached, my molecules are getting very complicated very quickly. If I have this triose system here, where I've got 3 alcohols, we call them trioses, then I've got 2 chiral centers. I could have 2 to the 2, I could have 4 possible isomers of that. If I move up to the tetroses here, I've got 3 chiral centers. All of a sudden, if each of those are chiral, I can have an isomer, a stereoisomer at each possible center, and I can get enantiomers, I can get diastereomers. It gets very complicated, right? So 2 to the 3 would be 8. And then if I go to the hexoses, and I start talking about glucose and galactose and biologically important carbohydrates that we're interested in, I've got 4 stereocenters. So now my possible number of isomers is 16. And I don't have any internal symmetry because that is not the same as that. Well, here's the answer. If you start drawing wedges and dashes for all of those compounds, you get lost very quickly. It is very, very difficult to do. So I think it relates kind of like the pKa idea. Why don't we use Ka? Why do we have to go to pKa? Because it's easier to remember. Once you understand it, they're easier to use if you bother learning them. This is similar to that. Initially, it is painful to get here to see what Fischer depictions are about, but ultimately, they are a much more elegant, faster way of communicating stereochemical information. So the definition here is on this slide, but I'm going to try and point it out here and then go back and do it in a bit more simple detail. Everything on the horizontal. Notice there are no wedges and dashes. That's the point. We've stripped out the wedges and dashes to keep it simple. Everything on the horizontal is coming out of the plane. Everything on the vertical, by definition, is going into the plane. And all of a sudden we have a tetrahedron. 2 wedge, 2 dash, that's a tetrahedron every time. So these depictions are trying to get rid of all of the noise that come along with wedges and dashes, and they are actually easier to understand and see once you understand it, once you get it. So there's something about this. This is pointing to the right, this is pointing to the left, the backbone. The carbon backbone is up and down, and you'll see that is very common. All the carbons are up and down in a line like so. We typically don't have carbons sticking off left and right unless it's an extra group. For carbohydrates, they're quite rare. So my functional groups stick off left and right. And I do put my hydrogens in to make sure that we recognize that they are there. So taking a step back, how do you build these things? Where do they come from? How do we manipulate them? And I said enjoy the weekend. Maybe not. Right? You've got to work this stuff out. Taylor. There are 1, 2, 3, 4 stereocenters, right? So 2 to the 4 being 16, I think. Yeah. You're not going to have to do 2 to the 4 on my exams. That would take forever. But 2 to the 2, 2 to the 3, probably. So that we understand it, so we can progress to the second semester, so we can get into biochem, pass biochem, get a job. Whatever it takes, right? You need to do these things. Here's the background. You take a chiral molecule like this, which is something quite simple, and you turn it in space so that all the carbons of the backbone are pointing up and down. So if I were to draw this out again, I would have a carbon chain at the top, I've got a methyl group at the bottom, I've got a hydrogen sticking out there, and I've got an OH group right there. That is a chiral molecule. And in a minute, we'll have to turn that into a wedge dash depiction and go in the other direction, which is not trivial at all. But Fischer said, since I'm dealing with carbohydrates, and I'm basically inventing biochemistry, I'm going to call them Fischer depictions. And I'm going to set them up this way. And 120 years later, we still set them up this way. Is that clever? Everything on the vertical, which are the carbon pieces of the framework, go back. Every time. Everything on the horizontal, which is everything else, typically hydrogens and functional groups, go left and right, as wedges. So if you set this up, you have the backbone up and down, which is where this comes from. That's tracing the carbon backbone. And on the left, we have a hydroxyl that goes over here. And on the right, we have a hydrogen that goes over there, with no wedges or dashes, because it gets too complicated otherwise. That's the definition. Everything on the horizontal is what? A wedge or a dash. Everything on the vertical is a dash. Every time. You might enjoy this stuff because when we get into mechanism next week, it gets really different. We have a definition. We can start drawing complex molecules, acyclic molecules, with this type of definition. And we can think about relationships. So all we have here are molecules that are related as either diastereomers or as enantiomers, and we've drawn them as Fischer depictions. So what is the direction in space of this hydrogen? Wedge or a dash? Wedge. And what about the R group up here? Dash. Now I'm going to ask you to do R and S on these things too. And we always do. You know, most people pass this stuff because they put the time in. If you look at this and you think about the ordering of this thing, I'll do some of these in the near future. This up here is a carbon of some sort. What's number 1 on that carbon? Br. What's number 4? Hydrogen. Now, think about what we did in class, and we did in recitation, and we will do again. What's the problem with number 4 if you think about solving this as a Carnegie Prelog system? It's coming in the wrong direction. It's coming in the wrong direction. So you have to either be good at imagining yourself coming from the other direction, or recognize that if I'm doing this, and I see clockwise, you are seeing what? Counterclockwise. Applying what we did to a more seemingly complex system. But right now we can use this very quickly. You'd be amazed how quickly you can draw these 4 pictures compared to drawing wedges and dashes. We'll see now that we've got 2. If R2 is not the same as R1, there's no meso possible, and so there's no internal symmetry. And if I put these 2 things together, they are mirror images. And if I pick this thing up and try and turn it like so, and try and put these bromines on these bromines, maybe that will work, but R2 will end up here, and they won't be superimposable. So therefore, they're not the same molecule. They are, in fact, enantiomers. Then I can start switching things around. If I look over here, I've got the bromine on the right up here, and I've got the bromine on the left over here. And it is not simply a rotation. I haven't rotated anything here. I've taken off 2 atoms or groups and switched them. By definition, that would then be stereoisomerism. But the point here is they're not mirror images. This one has both bromines on the right. This one has one on the right, one on the left. They can't be enantiomers, so therefore what's left is diastereomers. You are going to have to, for this next exam, for an MCAT, a PCAT, a DAT, an OAT, whatever you want to do in the future for standardized exams, know how to do this in your sleep. You will be doing it in your sleep. Ashley. If I think about, there's R2, here's R1. If I want to put my bromines on top of each other, I need to drag that molecule around like that. R2 ends up at the top. If you don't see this, you have several choices. You can sit there in ignorance, smiling at yourself, and we'll give you an F. Or you can get some help. And you'll be much happier if you get some help because you won't get an F. I shouldn't have to explain these things. That's the way it's going to work. So here we go. We have a system which is wedge dash. This is something you are familiar with writing so far, and all of you, because of Wednesday and Monday, should be able to work out the configurations, the R and the S. If I look at this system very quickly, what's missing from that carbon? Hydrogen. Is it a wedge dash or a banana? It's a dash, pointing backwards. So what's number 1? Bromine. What's number 2? The right-hand side of the molecule. What's number 3? Methyl. What's number 4? Hydrogen. Is the hydrogen in the correct orientation, yes or no? Yes, it is. So I do my direction in space, and I think bromine to here, that's where the R came from. Very quickly. If I think about this one, H, number 1, number 2, number 3, clockwise, this is in the correct direction, that's RR. What you are going to have to do is manipulate that to turn it into a Fischer depiction, and also go backwards from a Fischer depiction to the wedge dash depiction. And this is difficult. If you have the models, it helps, and if you can do this sort of thing, it helps. Right? I'll show you some tricks to be able to do this. So we're going to turn these things, first of all, into the series. We're going to recognize that if I have 2 chiral centers, then possibly I can get 4 stereoisomers. But does anybody see anything in this molecule? What's the potential in this molecule? Not necessarily rotational, but internal symmetry, right? One of these systems will be the same thing, and it's typically RS and SR. They tend to be the same molecule. So that's what we did with the meso. And then we can turn these things into Fischer depictions by doing this. I'm going to take a second here, and I'm going to try and show you this with Chem 3D, and then go back to that problem. So Chem 3D, what I've done here is I've set up just a molecule that has chiral centers. And I'm manipulating it in space so that I can think of it as a Newman depiction. If I want to make a Newman depiction, let's turn this thing on its end. There we go. Is that eclipsed or gauche or staggered? What is it? It's eclipsed. And if I draw this graph and I plot this graph, I can see the rotation around. Ignore the energies. This is not about energy. Just the fact that this allows me to rotate stuff, because I need to rotate stuff. If I get to here, what's that? Is that eclipsed or gauche or what is it? It's also eclipsed. What about down here? Give me a word that describes the relationship between the methyl at the back and the methyl at the top. Anti. So we know those things. What's the relationship between the green thing and the orange thing? Gauche, the language you should bring with you from the first exam. Well, what I need to do here is to manipulate this thing in space so that you can start to see, let's say, a zigzag depiction. If I turn this thing on its side like this, you can see the carbon backbone. Left, one here, 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 and here, is up and down and up and down. And you might have asked, why do we always draw it that way? And the answer is because they're anti The carbons are anti, and that's the best situation, right? That's why we draw them as these zigzag pictures, with the carbon backbone representing the ups and the downs. And then the functional groups and the hydrogens come sticking off of that, either left or right or back or forward. If I look at this molecule again, the orange group, is it pointing backwards or forwards? Backwards. What about the green group here, backwards or forwards? Backwards. I need to turn this into a Fischer so I can understand its three-dimensional properties and be able to solve these problems. What I need to do here is turn this thing and put the carbons up and down. That's all I've done, is I've manipulated it in space to put the carbon framework, instead of left to right as zigzags, I put it straight up and straight down. Okay with that? Turned it by 90 degrees if you like. If I start moving this thing in space, I'm trying to build a Fischer depiction. And what was the definition? The horizontals are what? The wedges are dashes. The horizontals are coming out towards you. So at the top here, for this chiral center, where I've got the little hand there, the bromine here to the left and the hydrogen to the right, they are coming out towards us. Is that okay? Yes, they are coming out towards us. That chiral center is fine as a Fischer depiction. When I start drawing this thing as a Fischer depiction, I can start thinking about this. Okay? I'm going to put my bromine on the left, I'm going to put my hydrogen on the right, I'm going to put my CH3 group down there. Now, what about down here at the bottom? Do I have a problem? Yes. Right? If you see this quickly, it's good. Whatever that green thing is, the fluorine and the hydrogen are pointing in the wrong direction. So I have a situation. This is where these come in handy. Right? The top two are coming towards us, that's fine. The bottom two are not. They're coming in this direction. What do I need to do? Rotate which one? Bottom. That's all you need to do is that. So again, if you're in the library, be very, very careful doing this. Right? You're going to be doing lots of this. People will think you're strange, but that's why we're scientists. Turn this thing around in space, all of a sudden you have a Fischer depiction. Where it was a zigzag like that, you turn it on its end, you turn it like that, away we go. That's all there is to it. I can do this on my model here by carefully rotating around here so that I end up with, where am I going to need to go to? Not there. I need to go to here, because now all my atoms on the horizontals should be coming towards us. Look at that. See it? Yeah? Maybe not perfect, but we're not far off. If I turn this slightly like that and I get the backbone organized straight up and straight down, there we are. That's a Fischer depiction. Ignore the energy. It's got nothing to do with energy. Fischer is not suggesting that this is the best, lowest energy system. They didn't know much about that back then. He's just saying that this is a very fast, very useful method of transferring stereochemical information from a piece of paper into your head. Joe?
So you had a
It is, and this is kind of useful because when you get to carbohydrate chemistry in my second semester and in biochem, carbohydrates do that and they cyclize. So yes, this backbone is starting to go back around on itself. And when you have a third stereocenter, you need to use your feet or something because you've only got two hands to be able to show all this happening. But you can do it sequentially, you can do it carefully if you ask questions and you follow what's going on. So what have I done here? I've tried to turn what was a wedge dash depiction in which the carbon backbone is up and down into a Fischer depiction in which the carbon backbone now is straight up and down. And then I fulfill the requirements because all my horizontals are coming out. If I turn it this way, they're coming out towards us, and away we go. That's what you need to do. And you need to go in the opposite direction from the horizontal zigzag stuff back to the wedge dash. So let's go back to this and see what I was trying to show here. I have a molecule, just chosen particularly this one over here, the RS, and I'm going to use this to show you where the Meso idea comes from and how the Fischer depiction helps you see that. Down at the bottom, this molecule here is this one to the top right. You should recognize, or you might recognize now, RS and SR actually will be the same thing. But how do we prove that? Because I can't see too easily that this thing is the same as that. Maybe if you manipulate it and turn it around, you'll see it's the same molecule. But I can use the Fischer depictions to do so. I'm going to rotate around that bond, and that's going to give me this. Now, in relationship for Newman depictions, what's the relationship between these two bromines? They are anti to each other, right? They're pointing in opposite directions. If I manipulate this thing around and I line it up like this so that my backbone is now in the same direction, what's the relationship between the two bromines? Eclipsed. It's eclipsed. And really, Fischer depictions are eclipsed. It's got nothing to do with energy, but if you want to relate it to something earlier, in terms of the shape of the thing, the Fischer depiction now suggests that things are eclipsed. As a quick way of writing these molecules. So there I go. Now I need to turn this thing up on its end, and in this case it doesn't matter because they'll both be the same molecule, but do we see a plane of symmetry now? You can very easily see that plane of symmetry for the Fischer depiction, which isn't so obvious for the wedge dash depiction. So this is why these things can be useful. Totally changed your lives today. You're welcome. For the better. So these are challenging, and we have to practice them. If we think about how to maybe go in the other direction, and how to worry about drawing different depictions, if I draw this, I have a plane of symmetry, therefore this equals this. That's a Meso system. On the left, this is not the same as this. This is the RR, this is the SS, and we have to be able to work those things out. So when we do RS and RR, I'm going to try this now. I'm going to give you a couple of examples, then we'll practice in recitation. You can come ask me questions. That carbon right there is chiral. It has 4 different atoms or groups attached. What's number 1? Br. What's number 4? Hydrogen. What's number 2? The bottom of the top. Bottom. And the top is 3. So my orientation right now seems to be 1 to 2 to 3, counterclockwise. But what's wrong with my hydrogen? It's in the wrong direction. So what's the stereochemistry? What's the configuration? Ah, that's where that came from. Down at the bottom, again, use an eraser, get rid of all that noise. Down at the bottom, I have a stereocenter. What's number 1? What's number 4? Hydrogen. What's number 2? Top. Number 3 at the bottom. I think I go from here to here to here, which looks like it's counterclockwise, but what is the issue? It's in the wrong direction. So you switch it and it's now R. That's where the RR came from. Go on. And that's something you've got to work on. Okay? That's something you've got to work on. If you go back to the system I drew on with the Chem 3D, they started out, I think, on the same side. They ended up on opposite sides. Right? Now, I can't do this in front of a big audience. I just don't have the machine or the device or whatever to do it. So if I'm standing like this and I'm in a wedge dash depiction, let's say these two here. Can anybody see that at the back? It's not very helpful, right? So my fingers that are coming towards you are moving. Now, if I do this, they're going to be on opposite sides. Here they're on the same side, here they're on opposite sides. That's a manipulation you have to see and you have to practice. I just don't have a good device to be able to do that. I moved one around to make sure that both of those horizontals are coming out as wedges. That's the definition. You will have fun with this. So the reason we're doing this is to prepare you for more complex molecules in the near future and to get you ready for biochemistry later on, which is many of you will have to do. So I'm going back now to this type of system. You can see now if I were trying to draw that as wedges and dashes, it would take me a while. If I draw it as these horizontals, understanding that they represent wedges and dashes, it's not so bad. So let's finish this off by just doing maybe R and S. Looking at this one here, what's number 1? O. What's number 4? Hydrogen. What's going to be number 2? The one with the 2 oxygens or the one with the 1 oxygen? Okay? It looks like it's going clockwise, yeah? But what's the problem? You need to practice that. If you can't do it, come and ask. It's a big chunk of the next test. Drawing these things, using them, applying them to the mechanistic ideas that are about to happen. So you can extrapolate this all the way through to the aldohexoses, which are very important in biochem. And as a test, see where you are in terms of understanding this. Give me the R and the S for all of those stereocenters. But you can do it, you can do it. Colleen. That's a very good question. If number 4 is in the horizontal, you should be looking from the opposite direction. But don't get lost here. There will be systems that aren't necessarily carbohydrate systems that we can make up, that 4 isn't necessarily in the wrong direction. If 4 happens to be, let's say down here happen to be 4, that's a dash, that's in the right direction. So you don't have to make an adjustment there. It's situation to situation. Michaela. One to 2 to 3. Yeah, counterclockwise. But I'm looking from the wrong direction because my number 4 is in the wrong direction. So if I see clockwise, what do you see? Counterclockwise. So it's all about recognizing that if you're looking from the wrong direction, you have to imagine yourself looking from the other direction, which is switching the answer. Did I? Sorry, my bad. So the point of today is to get you, remind you that, okay, you took an exam, and you're not allowed to take 3 weeks off now before the next exam. It just doesn't work like that. There are so many ideas coming up next that are going to be difficult that you have to get on these things as soon as you can. Again, the homework is meant to push you. Get the homework done so you're at least reading the material. Now, I'm almost done with this chapter. I'm going to spend a couple of minutes on a couple of slides, and then I'll finish up on Monday. But Monday, I'm into 6. We'll bring some scary music or something on Monday to just make sure people recognize that Monday is different. It will change your lives fundamentally. I need to turn this maybe into these things. This isn't easy at all. This is something you can practice over the weekend. If you don't like it, we can do some more on Monday. I've first of all got to look at this and decide, well, it's a Fischer depiction. My horizontals are wedges, my verticals are dashes, and I need to manipulate these things in space. And if my chiral centers are next to each other, there's a good chance that when I do my rotation, because I have to go backwards now from the Fischer, I have to go back from here within the same direction to here where they're in opposite directions. And this works remarkably well, actually. If you can do this, it works to help you out. I'm going to end up with my hydroxyls on the same side, maybe, on the opposite, in the opposite direction. So I can first off maybe draw the series. I've got here SR, RS, which you should be able to work out. I've got the SS and the RR as the other pair. The relationship between these two is obvious. Everything's a mirror, so they are enantiomers. Everything over here, left side, right side, this is over here, they are enantiomers. There is no symmetry because the top is not the same as the bottom, so there's no meso possible here. Now I've got my 4 molecules, and you have to practice turning them into these things. If you don't get this at all, if you are completely struggling with this manipulation in space, you have a way out. You are able to work out R and S, and if they match, they're the same molecule. And if they don't match after your manipulations, you take your eraser and you make them match. It's as simple as that. There are ways around this without being very good at 3D stuff. So we've just said that this is SR. If you can do this manipulation where the hydroxyls are on opposite sides, maybe when I do the orientation they end up on the same side, great. Here you can see they're on the same side. But you can test it very quickly. This is why you have to be fast at R and S. This one is going to be S, and this one is going to be R. And if you got it wrong, switch them. Take your eraser and switch them around so that it matches. That's how you can do this. And then you can finish this off with a series and recognize that these are the same molecule, as are these. These are still enantiomers, these are still enantiomers, and these are diastereomers. So we'll have fun with Fischer, and I'm going to leave it there for today. On Monday I'm going to finish that off. I have a couple of slides left, and then I'm into 6. So please get on this for your own good.